Unit 16, Day 4, last notes of the unit. Let me show this again in case some folks didn't watch the previous video. Today is continuity, tomorrow is review, Thursday is the test, and then we're kind of done with pre-cal for a little bit. Not done, but done for a little bit because we'll start the roller coaster project.
How many units are there?
So there's only one more after this one.
Um,
How many units are there? 17. It's kind of a half unit, but we'll call it 17. And man, we're getting there. 5 more weeks of school. 4 real weeks of school. 5th one of, see how you feel that week kind of a thing. All right, continuity. Huge deal in calculus. Very important in calculus. Because it's the criterion, fancy word, for several fundamental definitions and theorems, including the derivative. Like a lot of things in calculus start with if f of x is continuous, then there's a whole bunch of thens in calculus after that. But it starts with, is it continuous? And if it's not continuous, you don't get to use that theorem. So we need to have a pretty good understanding of what continuity is so that we can go on to the rest of calculus. In some sense, continuity is easy because it makes sense. In others, there's also a technical side. Let's do the makes sense easy part first. And I'm going to label these pictures A, B, C, and D because I'm going to refer back to them when we start talking technical stuff. All right, the question I'm going to ask you is it continuous at x equals a? Because usually we're concerned about continuity at a particular point. In fact, I'll put a at the same spot on each of the graphs. So here's graph 1. What do you think? Is the graph continuous at x equals a? At that spot right there, is the graph continuous? What do you think?
No.
Might help if I drew some more graphs. So let's hold that thought. Let me draw some more, and then you can think about what your answer is. Reconsidering your answer for A and for B. So let's answer graph B. Is it continuous at A?
No.
No, there's a hole there, so not continuous at A. It is continuous everywhere else. So this is more for calculus, but that means if we're concerned with what's going on the left side, then we might be able to use all the calculus things. But if we're concerned with what's going on at A, we won't be able to use all those calculus things. So it's not continuous at A. In fact, we call that a point discontinuity. I feel like most of the names today make sense. It's discontinuous at a point. Therefore, it's a point discontinuity. Graph C. You can probably guess already what's going to be happening here because there's a dotted line at A. Continuous or not at x equals a?
No.
Not continuous at x equals a. Want to guess what we call that discontinuity? There's 2 or 3 words. You might get it. Yeah, that's a good guess. Asymptote discontinuity. That's not it, but that's a good guess. Infinite discontinuity. because it's an asymptote, at an asymptote. If you said something like asymptote discontinuity, everyone would know what you're talking about. They would know, oh yeah, that's the picture that we're referring to. Let's go back to graph A before we do graph D. So now, do you think graph A is continuous?
Yes.
Yes. In fact, I'm just going to say continuous everywhere. It doesn't have any strange points. So it's definitely continuous at A, but it's continuous everywhere. Any guesses on the last type of discontinuity? That's one more that's not continuous. Can you think of another way to draw a graph that's not a hole, not an asymptote, but discontinuous? It's a shot in the dark here.
It'd just be like a circle, but like on the other side.
Like where it just doesn't take.
Yeah, like at all.
Okay, so we're like there's nothing at A at all? Like
Yeah.
there's no graph around A, like all the graph is like all the way on one side?
Yeah.
Like if it was like a,
Like x equals -2 or something.
Yeah.
Or yeah.
something like that. I guess we would say it's not continuous at A, but it also doesn't even exist at A. So let me clarify then. I want the graph to exist at A, but I want it to be discontinuous at A. So there needs to be a point there, but I don't want it to be continuous.
Just a point.
Just a point. That's a great question. I guess I would say that is not continuous if it was just a point. Not what I was going for, but accurate. Anything else? Like you've seen these, we don't see them often.
Would it be just straight line up or straight line?
So a straight line up and down would be continuous, right? Because you could like think about continuous as like, can you draw it without lifting your pencil? So I could draw a straight line, a straight vertical line, and that would be continuous. Or a straight horizontal line would be continuous.
What is that?
Let's see. So let's do it like
Oh.
something like that.
And that's our test.
Not continuous at x equals A. Any guesses for the name of that discontinuity? What's the graph doing there?
Splitting.
Splitting's not a bad word. Starts with a J.
Jumping.
It's jumping. That's a jump discontinuity. A jump discontinuity. Let's kind of jump ahead. The bottom talks about removable versus non-removable discontinuities. Graph B, that's a removable discontinuity. Because there's a simple way to remove the discontinuity. What would you need to do to sort of fix the graph and make it continuous? Put something in the hole. Fill the hole in. Fill the hole, and it's continuous. So that's like a fixable discontinuity, a removable discontinuity. That's an easy fix. Just fill the hole in, and you're good. And fill the hole in is sort of what you do when you factor the top, factor the bottom. If there's a factor that cancels top and bottom, and you cancel it, you're removing the hole. We didn't use any of these words, but it had a point discontinuity. If you cancel top and bottom, you removed the discontinuity. You filled the hole. Now, the other two I mean, you could fix them, but it would require a lot of work, and you would significantly change the function, right? Like I either have to, on this jump one, I either have to lower the whole thing down, or raise the one on the left, or somehow connect it. Like it's a significant change to the function. Same thing with the asymptote. I can't like just say, oh, let me just connect the dots there or something. Like those are non-removable, meaning non-fixable. Can't be fixed. So like there's a minor discontinuity in picture B. I can handle that. Picture C and D, those are major discontinuities. They're not fixable, and the fancy word is non-removable. Like you are stuck with those. All right, talk with a partner. I don't want to do that. Write your definition here. Let me give you the very informal definition, and then I'll give you the formal definition. So the informal definition, the one that you use to answer the question of is it continuous or not by looking at the picture, is can you draw the graph without making any breaks? Right? Can you just draw a continuous graph? Like with one pencil stroke, can you draw the whole graph? If you can, then it's continuous. Now, some of you may be trying to be creative on me here and say, if you're careful, you could draw this one without lifting your pencil, the one with the hole, right? Because you could go and make a little hole and then keep going. But that's cheating. That I don't mean like that. If you can smoothly, easily draw the graph without breaks, it's continuous. The formal definition is obviously a little more formal, a little more involved. It's a three-step proof. You don't like that word. For continuity. The good news is it's like the same proof every time. So it's not like in geometry when you have a proof and they're all different and they're all 14 steps long and this is the same 3 steps every time. You guys don't have to memorize this, but calculus students have to memorize this. Occasionally on the AP test it will say, use the 3-step proof for continuity to discuss blah, 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 blah. So they have to know this. You don't have to know it yet, but again, we want you to see it this year, so when you see it next year, hopefully a little part of your brain says, oh yeah, we sort of talked about that. The limit as x approaches a of f of x exists. So the limit exists. There's got to be a limit. Part 2. Actually, let's pause on part 1 and look at the graphs A through B. Which ones have a limit that exists at A? Graph A does. Are there any others? So that limit exists at A. Any of the other graphs have a limit at A? D has a right limit and a left limit, but it doesn't have an overall limit. Remember, a limit that goes to infinity doesn't really count as a limit. That's D and E.
So B.
You don't seem convinced. You're right, but you are not convinced. Do you remember that B, there is a limit as x approaches A. It doesn't get to whatever value this is, let's say 3. But the limit is 3, even though the function isn't there. So graphs A and B have a limit that exists. Now, we need to say something about B that makes it not continuous. So the limit exists, but it's not continuous. Step 2 is f of A exists. So which graphs, plural, because there's 2 of them, does the function exist at x equals A? A and D. So the function exists for graph D, but the limit didn't exist, so that's not continuous if we're thinking formally. Like informally, we could just look at it. Formally, function exists for D, but the limit doesn't exist. For B, the limit exists, but the function doesn't exist. For part 3, we need another graph to illustrate part 3. The limit as x approaches a of f of x equals f of a. That would only be part or graph A. Okay, the challenge for you is, can you think of a graph, there's not one up there, can you think of a graph that meets step 1 and 2 but not step 3? So I want to draw a graph that the limit exists, the function exists, but they don't equal each other. Can you think of a graph that would do that?
It would go like one side would be like that, and one side would be like a dot.
Okay.
Like the left half of C and the right half of D.
Okay, if I use C at all, though, I've got an infinite limit, and the limit doesn't exist. So
I mean,
C's out.
We would go, I guess it's the same thing as D.
Okay, let's start with graph B, or something close to graph B. So that limit exists. Limit exists. Check. I want the function to exist, but I don't want the function and limit to be the same thing. So let's just put a dot somewhere else. So now the function exists. So I meet step 1 and step 2, but that graph's not continuous. And the official sort of formal reason is that the limit doesn't equal the function. Right? Like the limit's equal to 3 and the function's equal to 4. So that's not continuous. So the 3-step proof for continuity. Limit exists, function exists, and they're equal to each other. Limit exists, function exists, they're equal to each other. All right, we've covered the removable, non-removable stuff. That's at the bottom. I just labeled the pictures. Basically, a hole is removable. Let's see, removable is a hole. Non-removable is asymptotes and jumps. Maybe. Because I can fix a hole by filling it in. An asymptote or a jump, I'm kind of stuck with. All right, let's do some example problems. I think the example problems are easier than the theory behind it. All right, state the value of x, if any, at which the function has a discontinuity. Number 1a. What do you think? First example, so you may not know. What's going on at x equals -2? There's a hole. Now, it doesn't really matter that whether it's a hole or like anything from the bottom is going to be a problem. This one happens to be a hole. And a hole means there's a removable discontinuity. In fact, that's usually what we do. We remove the hole and then deal with what's left. Like, so we have to remember that there was a hole there, but usually we remove the hole by canceling it out, and then we can work the rest of the problem. So, make sure I answered this question. At x equals -2, there's a removable discontinuity. But again, even if there hadn't been the x plus 2 in the top, that would still be a discontinuity. It would just be an infinite discontinuity, or an asymptote discontinuity, as you wanted to label it, which is a good label. Let's see, part B. So this is a piecewise function. So left of 1 I have one function, and right of 1 I have another function. So what point am I worried about, I guess? Maybe I should ask it that way. Yeah, x equals 1, I need to figure out what's going on. Like, there might be a jump. So how do I figure out if there's a jump or not? At 1. Let's see, I've got two branches. Let's find f of 1, so that would be branch A, because that has the equal signs. That's a little bit easier to follow. 1 squared plus 3 equals 4. Okay, f of 1 equals 4. For B, I can't really plug in 1 because it's not equal to 1, but I could say there's an open circle at x equals 1. So 5 times 1 minus 7, that would be negative 2. So I don't know what else is going on in this graph, but graph B is over there. Graph A is some parabola looking thing, but there's a jump. Jump discontinuity at x equals 1. So I basically check both pieces of the function at the point I'm worried about. Number 2. Okay, right now number 2 is the same as part B, so I need to change something on this. So let's make this 5x minus 1. So for number 2, make that second function 5x minus 1. And again, I'm going to call it part A and part B. Part A, we kind of already did this. 1 squared plus 3 is 4. For part B, I have to be careful. It's not f of B or f of x at B, because when I plug in 1, I've got to be on branch A. But I can say there's an open circle at x equals 1. 5 times 1 minus 1 is 4. So what does that mean? There's no discontinuities. So the graph changes at x equals 1. It goes from this line, let's see, that would be something like that, to a parabola. But they managed to tie them together, so we would say f is continuous everywhere. Because x equals 1 was our only concern, but when it worked out, we were all good. Number 3, a very popular calculus question. Find the value of the constant k that makes this graph continuous. So again, I got a part A and a part B. What value am I worried about? What x value might it be discontinuous at? Where does the potential jump happens at 1? So again, let's plug in 1 in A and B. So on branch A, it equals 4. On branch B, k times 1 minus 7, so that's k minus 7. And what do I want to be true if this graph is continuous? I want those graphs to, I want them both to go to 4. I want these two to be equal to each other. So if it's continuous, then k minus 7 needs to equal 4. Sort of make them match up. So k would need to be 11. Number 4. 1, 2, 3 problem. Which of the following is continuous at x equals 1? Well, let's factor this thing and see what's going on here. So number 1, I factor the top. X minus 1, x minus 1. X minus 1's cancel. What does that mean is happening on that graph? There's a hole at x equals 1. How do I find the y value of that hole? Do you remember? There's a hole at x equals 1. Plug it in. Plug it into what's left. So the hole came from this being canceled. Now if I'll plug it in, 1 minus 1 is 0. So the hole is at 1, 0. There's a hole there. The second half of the graph, or of the equation, maybe that fills it in, but that tells me when x is 1, the function is 1. So whatever else is going on, that is not continuous. So it had a hole, and they tried to fill it in, but they missed. Maybe that's the way to say it. Let's see. Oh, I can't even factor that. So where is this thing discontinuous? Yep, that would be an asymptote or an infinite discontinuity. But it said at x equals 1 is what we're concerned with. So this is continuous at x equals 1. So negative 1's a problem, but it didn't ask about negative 1. It only asked about positive 1. And then here's another one where we need to see if the left branch equals the right branch. We've got a potential jump situation here. So 1/2, 1 plus 1 plus 1. Half of 2 is 1, plus 1 is 2. And b is just 2. So we're good at 1. So 2 and 3. Continuity, holes, limits, all goes together. Let's just do 2 more and then we'll be done. We'll pass on number 7. What values of k makes f continuous? We've done this before. This is the same thing from earlier. I'm worried about 1/2, so I need those two things to be equal to each other at 1/2. So that would be k times 1/8 minus 1/2 k minus 1/4. If I plug in a half. And if I plug in a half to the second part, 32 times 1/4 minus 2. So let's see, k over 8 minus k over 2 minus 1/4 equals 32 divided by 4 is 8. 8 minus 2 is 6. Look at all those fractions. What could we multiply by? This is from last week. What could we multiply through by that would wipe out all of the fractions? What number is big enough to cancel an 8, a 2, and a 4? Yeah, just an 8. So distribute the 8 to everybody and then carefully figure out what cancels. So the 8 over 8 cancels. 8 over 2 is 4. 8 over 4 is 2. And then 6 times 8. Common mistake is to forget to multiply the 8 to the other side. So negative 3k equals 50. So k equals negative 50/3. And this was a bad problem because the right answer wasn't there. Shouldn't have made it a multiple choice question. Promise you're going to get a question like this. What value of k makes it work? Set the two branches equal to each other at whatever point you're worried about, and then figure out what k is. They could easily have fractions of that difficulty, yes. 8s, 2s, and 4s, yes. All right, 6 has a graph, so that should go quick. The graph of g, a piecewise function, is crazy looking. Which of the following statements is true? G has an infinite discontinuity at x equals 1. True or false? At x equals 1, there's an infinite discontinuity. Yes. I mean, one side's up and one side's down, but they're both infinite, so yes. Non-removable discontinuity at x equals negative 1. Can I fix that? I mean, there's like an open circle there, but it's a jump. I can't fix that. So that is a non-removable discontinuity, so that's true. I can't fix a jump. Question 3, or statement 3. G has a non-removable discontinuity at x equals 2. Wait, that just has the hole at x equals 2. So 3 is false, because that is a removable discontinuity because it's a hole, like a fixable hole. If they just draw the dot in the right spot, it wouldn't change anything, it would just fix the hole. So 1 and 2 were true. 7 is one of those 3 problems in 1. You plug in 3 in branch A and B and see if it works. Plug in 3 in branch A and B and see if it works. Plug in 3 in branch A and B and see if it works. Alright, so your assignment is worksheet 4 on continuity. There's a K question. There's another picture question with very similar to the practice problems we did. I'm also going to give you the review. Again, this isn't today's assignment, this is tomorrow's assignment, but some of you start looking ahead, or you have a tutor, or you want to ask me questions, or whatever. So I'm going to go ahead and give you the review, even though officially it's tomorrow's assignment.